Hi everyone, thanks for joining the London Machine Learning Meetup. We're going to make a start now. So today we have Irwan Bello, who's going to be giving us a talk about Lambda networks and scaling of vision architectures. Irwan is coming to us from Google Brain. I want to let you know as well that we're really grateful to Irwan because he hasn't been feeling very well over the weekend, and actually he's not feeling great now. So thanks everyone for coming along, and please everyone bear with us because naturally Irwan hasn't had as much time as we would have liked to get the polish on the slides, but I think it's going to be fine anyway. And then after 40 minutes talk, we're going to have a discussion kindly moderated by Gul Varol, who is coming to us, who's an assistant professor at the École des Ponts, Paris Tech. Sorry for pronouncing that so badly. We're going to do as usual, where if you guys can give your questions in the Q&A and raise your hand if you want to ask them at the end, and we're going to come to your questions at the end, and Gul will select questions or carry her own discussion at the end of the talk as well. I'll explain the details when we get to that point. But right now, I'm going to hand over to Irwan to give the talk, and for the audience, you just put your questions into the QA. And if there's anything you wanted to say to us, oh, by the way, I'm Martin Goodson. I'm from Evolution AI, the sponsors and organizers of the meetup. If you have any questions for me or any of the other panelists, just put that into the chat. But don't put your questions in the chat, put your questions in the QA. Okay, thanks, Irwan.
Great, thank you, Martin. Yeah, so as Martin mentioned, I'll be presenting two papers today. The first one is called LambdaNetworks, Modeling Long-Range Interactions Without Attention. And the second paper is sort of an empirical study of scaling of vision architectures. Most of the talk will be spent on LambdaNetworks because it's a little bit more complex to understand. But we'll have, a good 10 minutes on the second paper as well. All right, so let's get started. So this is the talk outline for LambdaNetworks. I'll start with a summary to sort of position the paper. I'll discuss the motivation for Lambda layers. So Lambda layers are sort of the innovation introduced in the Lambda network paper. We'll discuss implementation complexities, how to, like different scenarios when we want to work with structured context, and we'll review experiments from the paper as well. So Lambda layers are basically a new class of layers that you can use in your neural networks. And they work by first summarizing context into fixed-size linear functions called lambdas, and applying these lambdas to their respective queries. So this abstraction, as we'll see, is quite general. In particular, it sort of encompasses previous works such as channel, spatial, and linear attention. So altogether, Lambda layers offer a scalable alternative to self-attention for capturing interactions between inputs and structured contextual information. And the reason you might want to use them is that they scale favorably compared to self-attention, and they can handle general structures because they have an understanding of the internal data structure. With Lambda layers, I was able to get very strong empirical results on static visual tasks such as image classification and detection and segmentation. So the motivation for Lambda layers comes from some of the challenges that arise when trying to apply self-attention to images. So images are multidimensional, large, and structured. So by structure, I mean that there's an ordering of the pixels, and if you change that ordering, you lose a lot of the information. For example, if you take an image and you shuffle the pixels randomly, you might not be able to tell anymore what that image was about. So there are mainly two challenges that arise when you try to apply self-attention to images. The first one is that you need to understand positional information, because as I just explained, it's either at least helpful and probably even crucial to to have an understanding of relative position between pixels to be able to understand the content of an image. The second challenge is that memory is that attention maps, which are quadratic with respect to the input length, become prohibitively large because images can easily have 10,000 pixels, and so if you do vanilla self-attention on that, that becomes a problem, especially when you process a batch of images in parallel. So there are also some, either like previous or concurrent solutions that attempt to solve these challenges. The first one is relative attention, which is a few years old, which was first introduced in the context of NLP and then introduced for images by myself and some coworkers. So relative attention solves the first problem, which is to capture the internal data structure. So here, the relative position between pixels, but it doesn't solve the problem of attention maps being too memory expensive. Another solution comes from sparse attention, which can, so for example, you have papers that present local self-attention alternatives where the queries only attend to a local memory around itself. You also have axial attention, which where the query sort of attends sequentially over its row and column, and both significantly reduce memory requirements. And you can also augment these operations with positional information. However, both these operations are very slow on TPUs and GPUs, and so you run into the problem that you can't really scale them, and it's not super practical to work with. Lastly, you have linear attention, which is more or less concurrent to the LambdaNetwork paper, that solves the problem of attention maps being too memory expensive, simply because linear attention sort of bypasses the step where you materialize attention maps, but linear attention doesn't provide rich positional information. And so these shortcomings sort of highlight the need for an efficient relative attention mechanism that models dynamic interactions between inputs or queries and their context, while capturing internal data structure. So for example, as I said, relative position between pixels, and without materializing attention maps. And so this is exactly what Lambda layers do. So let's look at self-attention and Lambda layers and what they do. So on the left here, you have an example of 3 queries. So here, a query is basically a pixel, and their local context, which are just sort of a local region around each query or each pixel, which is sort of embedded within a global context, which is the entire image here. So in the middle, you have the well-known self-attention operation. Self-attention associates each query with an attention distribution over its context, which is also known as the attention map. And on the right, you have the Lambda layer, which instead transforms each context into a fixed size linear function lambda. So here, linear function is basically just a matrix, right? And that matrix is applied to the corresponding query. So this is the computational graph of the Lambda layer. So it looks a little bit scary, but I promise you, once you're a little bit more familiar with it, it's not too bad. So here in red, you have the queries. Again, those are just like pixel, with sort of different features. So each query is associated with a lambda function. And that lambda function or matrix is obtained from the context. And so on the left side, you have the context from which you compute keys and values, K and V, similarly to self-attention. But instead of multiplying queries by keys, as you do in self-attention, you multiply keys by values first. which is very similar to what linear attention does actually. On top of that, you have relative position embeddings in yellow, which are going to be useful to sort of capture, the internal data structure in the data, as I mentioned earlier. And so, because you use these relative position embeddings, you will have a different lambda function or lambda matrix per query, because each query position each query has a different position, and so different relative position with respect to the context. And because of that, each query has a sort of customized lambda function based on its position. So you apply the lambda function to each query individually, and that gives you the output corresponding to that query. So by doing so, basically this process captures both content-based and position-based interactions between the queries and the context, which is what we set to do, what we set out to do. And on top of that, because you multiply keys and values first, or position embeddings and values first, you do not work with attention maps, and so you sort of forgo this memory expensive like tensors that are materialized only like in the vanilla self-attention operation. So the lambda layer can be interpreted as follows. So first, you generate the lambdas from the context, and this is essentially summarizing the context into a fixed size linear function or a matrix. Alternatively, you can see this matrix as the set of its columns. So here, each column will be, a contextual feature. And so the set of these columns, or the matrix, basically represents the context in a way that can be queried. And so you query the context by simply multiplying that linear matrix lambda by the input query. And so this is sort of similar as performing attention with a fixed set of queries instead of the queries coming from the pixels. The second step is to apply the lambdas to the queries, and this step essentially dynamically distributes the contextual features, which are, remember, the columns of the lambda matrix. And now they are distributed based on the content of the query. And so, when you multiply a query by a matrix, the output is basically a weighted sum of the matrix columns. And so in the context of the lambda layer, this is just saying that the output is a weighted sum of the lambda matrix columns, which are, the aggregated contextual features. And as I said, this process captures dynamic content and position-based interactions without attention maps, which is exactly what we wanted to do. So this abstraction of multiplying queries by linear functions is very simple and very general, because it occurs whenever vectors are multiplied by fixed size matrices. And so it's no surprise that you can actually cast many well-known operations in that general abstraction. And so in particular, feed-forward layers, channel attention, spatial attention, and linear attention can all be viewed as specific instances of lambda layers. So for example, in a feed-forward layer, you multiply each pixel query by a learned but fixed shear matrix. Channel attention, for example, squeeze and excite, which is a very popular operation in modern vision architectures, multiplies each channel by a scalar. And so you can get that behavior with the lambda layer in the case where the lambda is diagonal and shared across positions. Similarly, spatial attention, which is just simply multiplying each pixel by a scalar can be viewed as a lambda layer, where the lambdas are scalars and depend on the position of the query. Lastly, linear attention can be viewed as just multiplying each pixel query by a shared context-dependent matrix, which is also supported in the lambda layer abstraction. So let's talk about linear attention briefly and see how it can be cast as a content-based lambda layer. So brief review of linear attention. So linear attention approximates vanilla self-attention with a linear cost operation by first interpreting attention as a similarity kernel between queries and keys, factorizing this similarity kernel with a low-rank kernel approximation, and then multiplying the keys and values first. And doing so bypasses the materialization of attention maps, which yields a linear time and linear memory operation. So this has been used in both vision and NLP, and there are sort of multiple choices for the feature function phi that defines this similarity kernel. But the problem with linear attention, which I mentioned earlier, is that it does not capture position-based information. And so the lambda layer can sort of be viewed as linear attention with relative position information, except that when you add relative position information, the operation isn't linear anymore. It still has better memory complexity than vanilla self-attention, but calling it linear relative attention would be a little bit confusing because it's not linear time, nor linear memory. All right, so let's look at the implementation and the complexities. So the computational graph that we saw earlier was basically just a bunch of matrix multiplication and addition. And so this can be very easily implemented via einsums. So you first multiply the keys and the values by contracting over the context spatial dimension, which is denoted M here. That creates the content lambda. So as I said, the lambda layer captures both content-based and position-based interactions. And actually, you can even sort of split internally the content-based and the position-based interactions. And so you work with the content lambda that will capture the content-based interactions, and position lambdas that will capture the position-based interactions. And because each query has a different position, each query will receive a different position lambda. So you get the position lambdas by simply multiplying the relative position embeddings with the values by again contracting over the context spatial dimension M. So once you have the content and position lambdas, you get the content output and the position output simply by multiplying the queries with the lambdas. So the space complexity of the lambda layer becomes k times n times n, where k is the query depth, which is a hyperparameter that you can specify. Typically in the paper it's 16 or 8, which is relatively small. N is the input length and m is the context length. In most cases they're the same. So basically you can sort of see this space complexity as some hyperparameter times input length times the square of the input length. You also have an additional term that comes from storing the lambdas. So here B is the batch, N again is the input length, K is the query depth, and D is the output dimension. And so B and KD in the space complexity just comes from having one lambda for each query. how many queries do you have? You have batch times input length query, and each lambda is k by d. The time complexity, I'll just skip on that, but it's basically batch times input length square times k by d. And so this contrasts with multi-head attention, where the square of the input length is instead multiplied by batch and number of heads. And so when you walk with not small batch size, this difference become quite relevant. So yeah, lambda layers have large memory gains over multi-head attention. And this is again because the batch dimension doesn't appear in the space complexity of the lambda layer. I mean, it does, but it's not multiplied by the square term, which is the problematic term in practice. Additionally, the position embeddings, which explain the k by n by m term, can be shared across layers, which saves even more memory. However, there's sort of a problem here, right? Is that so each lambda is basically the query dimension times the output dimension, because you get a query as input and you multiply it by a lambda and you get your output. And so the hyperparameters k and d sort of control the space and time complexity, but also the sort of representational power of the lambda layer. And so you cannot arbitrarily reduce them, because if you do so, you lose too much representational power. But if they're too big, well, since these terms appear in the complexity, that can be problematic. And so the solution here is to use multi-query lambdas. So what you want to do here is that you'll have multiple queries per input, and you will apply the same lambda to each input. And when you do so, each lambda can be smaller because they're applied to multiple queries. So this is what it looks like. So on the left, you have the sort of single query lambda layer, where the output depth is equal to the to one of the dimension of the lambda matrix. And on the right, you have a multi-query lambda layer. So in the example, you have 2 queries per lambda. And so this enables you to have the size of the lambdas and therefore complexities, both space and time. And, sort of anecdotally, it also works better in practice, just looking at accuracies on ImageNet, perhaps because some parameters are reused. And so this trick is actually also valid for linear attention. Like it's kind of random, but I don't think it's been noticed by linear attention works so far, and I suspect it can also help. So now briefly talk about some special cases. Introduce position embeddings, but without making any assumptions about the structure of the context. But in practice, there are many like inductive biases that you might want to work with because they help learning. So one such inductive biases is translation equivalence. So for example, in images, videos, even text, whenever the context is sort of a multi-dimensional grid, having your operation be translation equivalent, which means that if you shift the input, the output is equivalently shifted, can be a very strong inductive bias and help learning a lot. So how do you add that to the lambda layer? It's very simple. You just make sure that your relative position, that your position embeddings are translation equivalent, and this is why they're called relative position embeddings actually. And so this is just a constraint that you add on your position embeddings. Another inductive biases that is useful is locality. For different reasons. One is that there's a there's a cost to having global interactions in terms of at least time complexity, because sort of each interaction between pixel has a cost, just like it comes with a few operations. And if they're useless because the pixels are too far away, then maybe it's better to restrict your operation to only capture local interactions. Additionally, if the pixels are too far away, maybe the interactions between them in your data set is noisy, and you prefer not to learn that. So how do we restrict interactions to a local context? The first solution is to simply sort of zero out the relevant position embeddings. So you can just say, well, the position embeddings between pixels that are further away than a certain threshold is just 0. And that works, but the computations still occur. They're just being zeroed out, so you don't get you don't get computational benefits. The second solution is to use the lambda convolution. So it turns out that there's an equivalence between einsum and convolutions when you do an einsum with embeddings that satisfy translation equivalence, when you do an einsum with relative position embeddings. And so you can use that equivalence to implement a convolution that basically performs a lambda layer operation. So in particular, if you want to do a 2D lambda convolution that can be implemented as a 3D convolution or a 2D depthwise convolution, just check the paper for the details. But that flexibility, that equivalence gives you a lot of flexibility on whether you want to use the einsum implementation or the convolution implementation, and that might depend on your specific hardware and software stack. On TPUs with TensorFlow, I found it typically faster to use the global einsum implementation. But for example, let's say you're working on a mobile phone, you want a model that goes on mobile, and you really don't want to have these sort of extra zeroed out computations, then maybe using the lambda convolution is a better choice. So let's look at experiments. So lambda layers outperform convolution and attention mechanisms while using less parameters. For example, if you consider the ResNet 50 architecture and you replace the 3x3 convolutions by a lambda layer, you get a 1.5% improvement in ImageNet top model accuracy while reducing parameters by 40%. Lambda layers are also faster and more memory efficient than self-attention. And so, this is sort of by design, because as we saw earlier, lambda layers do not materialize attention maps. So for example, still in the ResNet 50 architecture with image size 224, which is sort of, the canonical computer vision or image classification example, lambda layers reduce memory consumption by 200x compared to global self-attention. So actually, you cannot do global self-attention on most hardware with the ResNet 50 at all resolutions. And that's 3.7 faster than local self-attention, which, as I mentioned at the beginning of the talk, tends to be quite slow on TPUs and GPUs. And so you sort of get the best of both worlds. However, it turns out that modeling global interactions is still quite slow, especially at high resolution feature maps. So for example, in the ResNet 50 at images 224, if you want to apply the lambda layer at your highest resolution stage, which is 56 by 56, having each pixel look at every other pixel is still expensive. And so you might want to use, the lambda convolution to sort of only restrict your operation to local interactions, or just use standard convolutions here and resort to a hybrid model. And so such hybrid models actually maximize speed accuracy trade-off on TPUs and GPUs. And so in this paper, I introduce a family of hybrid Lambda network architectures across various scales that reach state-of-the-art in speed accuracy trade-off. So in particular, you get roughly 4x speedups over EfficientNets at training, roughly 3x at inference on TPUs, similar or actually a little bit better on GPUs. And these architectures require less memory than EfficientNets. So some of these improvements are due to improved scaling methodology, which is actually the second paper I'll present. When you train on extra data, such as JFT, which is a private data set with, I think, 300 million images, you also get really large speedups. So in this case, you get, so I don't remember, yeah, 9.5x speedups over the largest EfficientNet, which is trained the same way, and 9x speedup over a vision transformer with similar accuracy, which is trained a different way, but still using extra data. Lambda networks also get very strong parameter efficiency results because, most parameters only come from these position embeddings, which are very light compared to, compared to a standard convolution. And so, for example, you're able to match or improve upon flops and parameter efficiency of large EfficientNets with LambdaResNets, which is all significant because this is what EfficientNets, EfficientNets were designed to minimize flops and parameters. You can also use LambdaResNets as backbone of a mask or CNN architecture, and that leads to sizable improvements, especially for small objects. So, for example, you get like 1.8 MAP bounding box improvement on small objects just by switching the ResNet from the ResNet 101 to a LambdaResNet 101. Right, so we don't have much time left, but let me present the second paper, which is just called Revisiting ResNets, Improved Training and Scaling Strategies. So the performance of a vision model depends on a few different factors, namely the architecture, the training methodologies being used, and also the scaling strategies. So both the scaling strategies and the scale of the model. And unfortunately, many papers do not really disentangle these three factors, which makes it hard, for researchers and practitioners to gauge where the improvements come from. So we wanted to see what happens when you actually disentangle these three factors carefully. And by doing that, we drew several, conclusions, some of which are perhaps surprising. So the first one is that architectural changes matter much less than training and scaling strategies. We also find that previous works on scaling vision models have made suboptimal decisions. Simple ResNets are still quite competitive when properly trained and scaled. And the last observation is that supervised learning, when you use improved training methods, actually outperforms results from the self-supervised learning literature. So on the left, you have a Pareto curve of models, of a family of models called ResNet RS, which are just ResNets that are trained properly. So by trained properly, I mean trained with sort of modern training methodologies such as data augmentation, stochastic depth, dropout, and so on, because when the original ResNet paper came out, a lot of these methods weren't, didn't exist or weren't used widely. But newer works, when they report the papers, used, all these techniques, and so it makes comparisons a little bit harder. And in particular, we find that just training and scaling ResNets properly leads to 2 to 3x speedups on EfficientNets. And so that kind of, this observation really highlights both the difficulty and the importance of comparing architectures properly. We also get a 5x speedup in semi-supervised learning, so the NoisyStudent paper. And so again, this sort of shows that a lot of the architectural innovations since the ResNet are at least haven't been that important, or matter much less than proper training and scaling strategies. So the improved training methodologies here are just a combination of well-known regularization techniques and training techniques. And so the first trick is to just train longer. And our recent papers do that, but some papers unfortunately still compare against the the sort of original ResNet result, which was trained only for 90 epochs. But if you train for longer with improved learning rate decay, you use label smoothing, stochastic depth, data augmentation, dropout. You also decrease the weight decay, which enables to use more other regularization techniques. You can take a ResNet 200 from 79% to 82.2% through training methods alone, without any architectural innovations. And then if you add squeeze and excite and ResNet D, which are two popular architectural changes that are widely used today, you get an extra 1.2% improvement. But observation here is that 3/4 of the gain is obtained through improved training techniques alone. So next we look at scaling. First, scaling of the flops versus the ImageNet error. And so we observe that the error scales as a power law with flops at small scale, but that trend breaks at larger scale, which is sort of a deviation from the scaling law papers. And so we think that this is because we're an ImageNet where the data is bounded and we go over the data many times, and so overfitting can be an issue. But the fact that flops do not accurately predict performance at larger scale means that the specifics of the scaling configurations actually matters. So whether you scale the depth, the width, or the image resolution is important for the final scale accuracy trade-off. So we look next at the error versus latency, and we find that the best performing scaling strategy actually depends on the training regime. So on the left, when you train for only 10 epochs and overfitting is not really an issue because you don't go over the data set that many times, we find that scaling the width is preferred. But on the right, when you train for 350 epochs and overfitting is an issue, even when using regularization methods, we find that scaling the depth is always better because scaling the width is prone to overfitting. And so we recommend the following scaling strategies: scale the depth if overfitting can occur, scale the width otherwise. This actually matches what previous walks have done. So typically walks that train on JFT, which is a very large scale data set, scale the width. But there were no sort of previous studies as to why they were doing so. Additionally, we find that scaling the image resolution leads to diminishing returns, and so it's better to scale the image resolution very slowly compared to prior walks. So many prior walks, such as EfficientNets or TResNet or ResNets, use image size, in the 400s or even 600s. We find that there's no really, it's better to avoid going over 400 by 400 image sizes, at least for classification. So just to exemplify I think the fact that ResNets have been better than EfficientNets all this time, and I think this was known by a few practitioners, but not by the wide community. I think it's an example of the difficulty and the challenges of properly comparing vision architectures. And so to properly compare vision architectures, we need to control for scale and training. So controlling for scale can be done via a few different metrics. A lot of papers report flops and parameters, but unfortunately, flops aren't a good proxy of latencies on hardware such as TPUs and GPUs. And similarly, parameters aren't a good proxy of memory usage, at least at training, because memory can be dominated by activation. And so this table here sort of exemplifies that. If you take a ResNet RS350, it has almost 4x the number of parameters and 2x the number of flops as EfficientNet B6, but it is 2.7 times faster and requires 2.3 times less memory. You also need to control for training methods. So, if your baseline should be trained a similar way, you should also try to tune your baseline as good as possible. And unfortunately, a lot of researchers tend to not necessarily do that due to incentives and publication pressure whatsoever. There are also a lot of common presentation tricks and gotchas. So basically, when you write a paper, you have a series of presentation decisions that you need to make, and researchers tend to make decisions that will put up their methods in a good light, and I think that's fine. Some of these decisions are okay, some are more borderline, and some are like kind of bad. So some gotchas that I've seen recently is that people will report accuracy and latency at different image sizes. So for example, they'll report training latency at image size 224, but they will plot the accuracy at resolution 320, because when at inference you can sort of change the input image size, but when you just see that on the plot, I think most people sort of don't understand, don't necessarily see that this trick is being used. And so I think this is used in the NFNet paper and also in EfficientNet V2, and this actually explains like a roughly 2x speed up over the baselines. So unfortunately, people are starting to do that now, but that's just one of sort of presentation tricks and gotchas that researchers use or accidentally use. And yeah, so I think this is my last slide. So, I presented sort of this improved training methodologies, which is just a combination of well-known augmentation and training methods. So another issue in the literature is that self-supervised learning works tend to compare against supervised learning without any improved training methods. But self-supervised learning also trains for longer. They also use data augmentation. They have, maybe this temperature hyperparameter that looks like label smoothing. And so these comparisons are also a little bit shaky, or at least difficult. And so we find in that paper that if you do an apple-to-apple comparison, it turns out that supervised learning, rivals or outperforms results from the self-supervised learning literature, which is, I think that's fine, because supervised learning does require access to labels, but I think it's worthwhile to mention because self-supervised learning sometimes claims that they yield more universal representations than supervised learning. So yeah, that's my last slide, so we can move to questions.
Well, thanks for the great talk. I'm going to introduce Gul again, who's going to conduct the moderation of the discussion. Guys, I can see there's a few questions. If you can raise your hand, then just as usual, we're much more likely to ask your question if you raise your hand. But otherwise, I'm going to hand over to Gul. Thanks, Gul.
Thank you. Thanks for the nice talk, Irwan. And there were actually a few questions which are related, and I wanted to ask about that as well. So I'll just combine them into one. So you designed something which is basically for vision. Well, at least the way it's presented, the experiments and the data sets were used in vision, but it's something more generic than that. And then you say it's useful for structured data such as images. Can you comment on what other data types this is useful and what other data types that are not useful? Especially there was a question about NLP and language modeling task, and I want to add 3D data and video data to that.
Yeah, so my intuition, I mean, again, the motivation was really to apply it to structured data. And so the bet for Lambda layers is really that relative position embeddings are important for images. So for example, for NLP, you can try Lambda layers. I mean, there are sort of different levels of answer to that question. But for NLP, if you randomly permute words in a sentence, you can still do pretty well because language isn't as structured as images. Really, if you take an image, you permute the pixels, you will have no idea where it is. If I give you a 10-word sentence and I permute the words, you can still infer what's going on. So relative position embeddings aren't as important in language modeling. And so I think that's the reason why computer vision was a better domain to showcase the benefits of Lambda layers. The second reason is that now if you want to get some attention with papers in deep learning, you need very strong empirical results. And so myself, I haven't worked that much with language modeling. And so it means I won't be able to get very strong results with language modeling, irrespective of the idea, even if it's great, because a lot of these things, you need to tune the models, you need to understand the task really well. And so, even if the method is great, it's kind of sad, but basically you can't get good results in a task that you don't get time to familiarize yourself with. And so, if I gave myself 6 weeks to try Lambda layers on NLP, I don't think I would get very good results because that's not enough time to get good at the task. Whereas, I've worked a lot with image classification, and actually the story of the second paper on ResNets is just that I was trying to get better results with LambdaNetworks, and I realized my baselines were getting really good compared to the literature. And that's how I realized, well, actually, if you train ResNets well and you scale them well, you can get really good results. So I think there are two reasons why I didn't try NLP. First is that, the main benefit of Lambda layers is understanding the internal data structure. And I think that's less important for NLP. And second, to get good results, you need familiarity with the task. And I don't have that at the moment.
Okay, so it seems somebody needs to try, and then we'll learn.
But for NLP, there's linear attention. I think there's a lot of literature that is very close. As I mentioned, Lambda layers are very close to linear attention. It was kind of concurrent, but maybe today, if I rewrote the Lambda layer paper today, I might, make a lot of different presentation choices and really anchor it as, efficient attention with relative position information or something. But yeah, for 3D, I think that's interesting. I'm actually in the process of trying stuff in that domain. But basically, I think they are really good for any task where the data structure is really important, and that can be speech, that can be vision, but NLP, I think, a little bit less so compared to linear attention.
Thank you. Okay, I guess that answers quite a few of the questions. Let me move to Herbie's question, Okay, so they say, you mentioned that speedups of Lambda networks were greater on larger data sets like GFT. And why do you think this happens compared to ImageNet, I guess?
Yeah, that's a great question. It's due to, essentially, it's due to people who, okay, so essentially it's due to GFT being a less competitive task because it's a private data set. It takes a lot of resources to run. There are way less results on GFT than there are on ImageNet. And so I think this is just due to people having tried less things and just the best numbers on GFT being less good. And so, for example, the VIT paper, they had state-of-the-art results on GFT, But if you think about it, like how many papers have reported results on JFT before VIT? There were 2 papers. One was the BIT paper, which is the same team. And the other one was EfficientNet, the NoisyStudent paper, using EfficientNets. And so it's also another thing that you sort of develop a taste for as a researcher, is that you know that certain tasks are very competitive and some aren't. So the reason why the speedups are greater on JFT is just that the task is less competitive, or at least was less competitive at the time.
Okay, so you're saying it hasn't to do with being larger scale data set or not? It's more about.
Yeah, I don't. I mean, I think there may be some of that, but it's, you know, that's really negligible compared to just the task. I mean, basically, you know, a good example of that is that the properly trained and scaled ResNets get 5x speed up over EfficientNet NoisyStudent, and they get 2 to 3x speed up over supervised EfficientNet. So you have the same thing. It's just because the NoisyStudent results aren't that good. Same, the VIT results aren't that good just because the task isn't as competitive.
Okay, makes sense. But about that part of properly training, I don't know, maybe you have them already on your paper, but a lot of the experiments were on ImageNet. So do you think there was some also, like, is this training strategy, is it generic to all the data sets, or is there some overfitting going on ImageNet as well?
I wouldn't call it overfitting, but yeah, the training hyperparameters are sort of customized for ImageNet, or at least data sets that have similar size as ImageNet. Okay. And so, for example, when you train on JFT, you don't need the regularization techniques that actually help.
Okay, so the list of techniques, strategies that work for ImageNet, you wouldn't like take them as they are for bigger data sets.
Yeah, exactly. I mean, I would sort of, you know, work with the same techniques, increase regularization if the data set is even smaller, remove or decrease or remove regularization when the data set is larger. Also, as I said, on large scale data sets, you want to scale the width instead of the depth. But yeah, that's a little bit unsatisfying because, you know, it doesn't provide sort of general answers. But I think the reality is just that the best scaling decisions and even the best training decisions depend on the regime and the data set size you're working with. And I think that's kind of expected as well.
Yeah, it's kind of annoying as well. So like when you said self-supervised methods are not universal, as they say, is there a chance that they're actually more universal, but so in terms of training strategy, there's something more generic in them across data sets?
I mean, I think when you do, so I don't have that experience myself, but I suspect that when you use self-supervised learning, the hyperparameters will also depend on the size of your data set. So I think that's kind of the case for every training paradigm. Again, you know, you know, self-supervised learning doesn't require labels. So it's not a problem that it is slightly outperformed by supervised learning. If anything, that's kind of expected. I think the point of that table is just to show, you know, I mean, the second paper, Revisiting ResNet, is kind of positioned as a strong baseline paper. There's not really any innovation in it. It's just like a careful empirical study and saying, hey, like, you know, a lot of these architectural papers are kind of bullshit. You know, you can get the same results or better results by just using ResNets, which have been, you know, widely used for 4 or 5 years. Same, a lot of these self-supervised learning papers, or at least results, aren't as strong as they claim to be. And, you know, if you read some of these papers, it's kind of insane. You're like, wow, like SimCLR v2 is better than self-supervised learning. Like they get the same result as supervised learning with 10x of the data set. And if you're familiar with the test, you're like, no, that's really not the case. So I think the paper is just, you know, it's just trying to sort of highlight this. And I don't think this is just, I don't think this is just true in image classification and self-supervised versus supervised learning. It's just the task that we were sort of working on at the time.
I mean, it's valuable to have the controlled experiments. I think there was a similar paper for metric learning as well, a reality check of controlling everything. So I think Zach had raised hand. I don't know if I should read the question instead. I think it's on QA now. How do your Lambda networks compare with EfficientNet after you remove EfficientNet's poor choice of image resolution? Because when you compare them, they were at different resolutions, but then you said it matters to have the right resolution.
Yeah. I mean, so in the second paper, we have sort of a Pareto curve with properly scaled EfficientNets. And so, yeah, when you reduce the resolution in EfficientNets, that makes them better on the speed accuracy Pareto curve. However, they're still worse than just ResNets. And so because LambdaNets are better than ResNets, LambdaNets are also going to be better than properly scaled EfficientNets.
Okay. That makes sense.
And so the reason why that's the case is that EfficientNet uses depth-wise convolutions, which aren't good for GPUs and TPUs. We sort of explain it a little bit in the ResNet paper. Essentially, it's that the inverted bottleneck that's used in depth-wise convolutions require larger activations, and so you need to load these activations into memory, and this is where most of the latency comes from. So it's better to have dense convolutions. And now you have EfficientNet v2, which sort of takes all these things together and sort of got rid of all the bad choices in the original EfficientNet paper.
Okay, I think there's a related question, but I'm not sure if that answers because I'm not familiar with those numbers. I was surprised at the latency comparison of efficient B6 versus RS350. And what is RS350 and why did it beat B6?
So ResNet RS350 is just, we just named them by the number of layers, modulo 1 or 2, I think. So ResNet 350
layers.
Yeah.
Okay.
So ResNet 200, it's 200 layers. And, in that paper, we said you want to scale the depth, at least on ImageNet, when overfitting can be an issue. And so we also introduced, I think, ResNet 270, ResNet 350, and ResNet 420. So that's just like a deeper ResNet. Why did it beat EfficientNet B6? Again, it's just ResNet. ResNets are a better model family than EfficientNets on TPUs and GPUs. Also due to the bad scaling of EfficientNets, to the use of depth-wise convolution or inverted bottlenecks. And it's only it may be surprising because the EfficientNet paper compared against non-scaled ResNets or not properly trained ResNets, but if you do an apples-to-apple comparison, those are the results.
Okay, I think that's a good place to stop maybe and not keep you more tired. But yeah, I think the main message has been make apple-to-apple comparisons, and I guess that's gonna be the case in the near future more and more.
Yeah, let's hope so.
Thank you so much, guys. Thanks everyone for a fantastic talk, and thanks Gul for conducting the QA for us today. I really appreciate it.
Thanks for organizing.
Thank you. Thanks to the audience for coming along. We do actually have one question that I wanted to answer. So this is from Usman. Can we get the link to the recording afterwards, please? Yeah, we are recording this. So as usual, we're going to post it to the YouTube channel. If you go to YouTube and search for London Machine Learning, or maybe London Machine Learning Meetup, if you need to, you'll find the channel. Just subscribe to the channel, and then you'll get the alert. Otherwise, just connect with me on LinkedIn at Martin Goodson. I'm sorry, on Twitter or LinkedIn at Martin Goodson, and I'm going to let you know when we post it. But we're going to post it probably like tomorrow, something like that. Thanks again, everyone, and take care. See you next time. Bye-bye.
Bye, everyone. Thank you.
Bye.